Okay, good afternoon. Can you hear me? Okay, thank you. So today, we continue to talk about the exercise on transformers. You still remember that, okay? In last week, we talked about the example 1 to example 5 in the exercise. And for the example 5, actually, we are start talking about the practical transformer, which involves the internal impedance and both the primary and secondary. And their relationships, right, between the terminal input voltage and the internal induced voltage. We have very clear, right? So calculations based on one example given here. And once again, let me try to draw the so-called, right, the practical circuit to showing you the relationship between the terminal input voltage and the internal, right, induced voltage here. And generally, for a given transformer, it has the input side with the input impedance, leakage reactance, and the magnetizing parts. And similarly, in the second parts, they have the magnetizing reactance, they have the leakage reactance, they have the internal copper resistance, and looking here, so this is output. So generally, suppose the input current at the primary, say R1, I1, resistance R1, and the leakage reactance X1. Similarly, we have the X2, R2. Look at here, the currents outputs. Outputs. So we have the inputs voltage V1. So we have output voltage V2. So pay attention to the arrow's direction. So because we based on arrow direction, suppose that represents the practical, right, relative direction, we do the calculations, right, showing the solutions. So here is the internal induced voltage on the primary side. Here is the internal induced voltage on the secondary side. The transformation ratio this is the relationships. Generally, we also has the core losses here. Okay, so this is a complete, right, a separate circuit describing the relationship between the primary and the secondary with their individual, right, parameters drawing there. So primary, so we have the terminal input voltage V1 here. We have the terminal input current R1 and the internal copper resistance R1, internal, right, leakage reactance X1, and mutual reactance or magnetizing reactance XM1 here. So this generally is the magnetizing reactance XM1. Okay. And this is the M2. Of course, XM1 over XM2 will be the transformation ratio. Okay. Okay. In such a way, given that the secondary output currents, the secondary output voltage, the internal impedance, then you can estimate, right, based on the ratios, you can estimate internal voltage drops, internal induced voltage, and right primary input voltage and current, and so on. Okay, so this is a revision on the example 5 we learned last week. And once again, pay attention to that here. So, and the part E, as you found that, so the ratio between the E1 and E2, the ratio between the V1 and V2 is a little bit different. So in practice, we use, and generally we define the input terminal voltage and output terminal voltage, their ratios as the practical ratios. Although they are slightly different, between the V1 over V2 and U1 over U2. Okay. So here show the relationship of it. Now come to the example 6. That showing you how to define the internal impedance referred to primary or referred to secondary. Also, right, based on the example 5. Okay, so here, because that we would like to clarify to you different concepts used in analysis of transformers. So we still, based on the example 5, looking at example 6. So example 6 tried to write once again to highlight to you the concepts of the equivalent internal resistance, equivalent internal reactance, equivalent internal impedance, referred to primary and referred to secondary, so that you can have a clear, right, understanding of this kind of concepts. Now, we have a quick look at the question itself and the solution here. Learn how to, for any kind of the transformers, to find out the equivalent, right, internal impedance issue. For the transformer given in example 5, calculate A, the equivalent internal resistance referred to the primary, B, the equivalent internal reactance referred to the primary, and C, the equivalent internal impedance referred to primary. Okay, pay attention to the wordings here. D, equivalent secondary load impedance of 0.1 ohms resistive referred to the primary. And F, primary load current if the primary voltage is 2,300 volts. So here, is a demonstration that, for the A, equivalent internal resistance refer to the primary, that is the primary resistance, the original values, plus the transformation A squared times the secondary resistance. You will find that primary 0.1 ohms. Secondary refer to primary now will be 0.1 ohms too. In total, 0.2 ohms. So the features reflected by this, right, is generally applicable to most of transformer. That means the primary and secondary, their resistance has a relationship like this. For example, if the primary is 1 ohms, secondary, they're referred to primary will also be 1 ohms or something like that. Okay. This is right general situations. Now, similarly, so for part B, the equivalent reactance refer to primary. So that is the primary leakage reactance, no change, original values, and the secondary leakage reactance times the transformation ratio square. So that is the equivalent 1. Similarly, that you found that the primary, which is the high voltage side, has a reactance 0.3 ohms. And the secondary, which is the low voltage side, has a original reactance 0.003 ohms. But refer to the primary, that means the refer to the high voltage side, also becomes 0.3 ohms. To here is 0.6 ohms. Okay. So generally, why like this? Because actually, I already explained to you right in previous one. Because that the primary high voltage we use more turn numbers. The secondary low voltage we use less turn numbers. So you know the reactance proportional to inductance, inductance proportional to turns, turn number square, right? Turn number square. And the voltage ratio, that proportional to numbers ratio. That's why there is a square, right? A square. Okay. C parts. Okay. So when we're talking about the internal impedance refer to primary, so you must combine the resistance, both the resistance and the reactance. You write them separately, or write them into a polar form, or write them into a complex number form like this. So here we write in the complex number form. So the resistance 0.2 ohms, the reactance 0.6 ohms. Okay. So they have 0.2 plus J 0.6 ohms. Okay. J 0.6 ohms. Their total values 0.632 ohms. Of course, their impedance angles can be found out here. Similarly, okay. So these examples just ask you to find out the values referred to primary, but how about refer to the secondary? So what will be that? Okay, what will be that? So when refer to secondary, so the impedance equivalent, refer to secondary. So equivalent, refer to secondary. So you can refer to secondary. That is the primary. For examples, the resistance, refer to the secondary plus and primary over the transformation ratio A squared. Okay, so when referred to the secondary, they will change, right? They will change, right? Change. Similarly for the reactance, similarly for the impedance. Okay. For the load, that when the secondary, okay, and to the secondary, if we have a loading that has 0.1 okay, ohms, then we refer to the primary. That means when you're looking or measure and the primary side of transformer, so the internal, okay, sorry, the loading impedance, okay, looking at the primary side will be the okay, impedance looking at the secondary side times the transformation ratio square, A square Z loading. Okay, so here, given that 0.1 ohms loading at the secondary, transformation ratio is 10. So when it is referred to primary, it becomes 10 ohms. Okay. Similarly, if you have the impedance at the high voltage side, where we refer to low voltage side, the impedance will become smaller. Okay, that's smaller. Okay. Now, so the part E, okay, the part E, okay, okay, E that actually is the F, right? So the F, right here, E, right? Okay. So given that the secondary, okay, loading impedance is 0.1 ohms, when referred to primary becomes the 10 ohms, right? Which is resistive. And the internal resistance of the transformer, which is given, okay, estimated, and part C refer to the primary 0.632 ohms that get with impedance angles. So when referred to the primary, so the total voltage and the primary is 2,300 volts, which is fixed. Okay, so the input currents I1 not equal to okay, V1 over the total impedance refer to the primary. So if we draw it into a circuit, that will be like this. And the excitation branch is ignored because it is the impedance of the excitation branch is very big. So here is the resistance equivalent referred to primary. This is the reactance equivalent referred to primary. This is the transformation ratio A squared that the loading impedance, okay, loading impedance. Okay, so the excitation branch could be ignored. So the total input voltage V1, the total input current R1, and all the internal resistance impedance refer to primary, and the loading impedance also refer to primary. That's the circuit. You're looking at this circuit is very simple, right? Okay. Straightforward, simple, right? So that's why we have the internal, so a primary input currents, that primary input voltage over the total impedance referred to primary, which once again involves both the internal impedance of the transformer. Okay, here we use the Z1 represent, and the secondary load impedance referred to primary, which here is A square ZL. And in the ABCD, we already found out the values of the ZE1 and A square ZL. We just need to break them in. So we can write further to write into the impedance, okay, reactance, impedance, okay, resistance, reactance. Okay. Here, look at here, pay attention to these parts. Okay. So plus minus here sometimes depends on the power factor of loading. Okay. Plus for leading power factor negative for lagging power factor Okay, so look at here. So, generally speaking, that the input current is the voltage over the total impedance. Here, the impedance including both the transformer itself impedance and the loading impedance and the secondary. But practically, so because you have the resistance and the reactance. For the reactance parts, right? For the loading parts, the load has different power factors. So the for the reactance parts, so plus minus, look at here. So the plus for leading power factor, which is capacitive loading, and minus for the lagging power factor, which for the inductive loadings. Okay, here the question telling you that loading is a resistive one. That means the power factors is 1. Okay, it's 1. Here it is minus, right? Reactance values is 0, right? Value is 0. Okay. XL is 0. XL is 0. So we bring in that the resistance, equivalent resistance refer primary 0.2 ohms transformer, resistance of loading 10 ohms refer transformer, and the reactance the transformer 0.1 refer to primary, and the reactance of loading refer primary to primary is 0. So we can calculate the values, as well as actually, if necessary, you can find out the phase angles. So this is the values of it, and also phase angles. So here we do not show the phase angle because single phase transformer. So we just concentrated on the values here. So if when necessary, phase angles, you can write out. Okay, so example 6 actually is a continuation of example 5. So basically, try to draw your attention to how to use the equivalent internal impedance concepts to in practice to estimate the input current, input voltage required. Okay, but here, so given that the input voltage and the loading are the secondary, so ask you to calculate the input currents. But if given that the secondary loading, given that the secondary required voltage, okay, so or required currents, that how to estimate the required input voltage. Okay. Okay, so a question raised that, so similarly, we can check these examples. So if the loading impedance and the current required is given, so what is the input voltage required and the primary? Okay, so this is given that the primary input right voltage. Okay, primary input voltage. And estimate the primary input currents. Now, question change. Given that the impedance of the secondary loading and fix the current required, that what is the input voltage required and the primary. So you can do it as an example, right? So by yourselves, okay? Because we cannot list all the possible questions at this moment. Okay, but you should know the relationship here. Similarly, you can use in this one, right? Okay. First, you should estimate the current. Then your impedance given, you can estimate the voltage, right? Current voltage, right? Their relationship given here. Their circuit given here. Okay, this is a general case. Okay, so now we're looking at two examples that are talking about the testings. So the usage of testings and also the basic connections when doing the testings. Example 7 that is showing you how to do the short circuit tests. Okay, for a given step down transformers. So as we show here, so we have step down transformer, so 2,300 volts primary and 230 volts secondary, and a rating 20 kVA step down transformer is connected as shown in the figures. So with the low voltage side short circuited, and short circuit data obtained for the high voltage side are given here. So we show here. So low voltage side with less turn numbers be short circuit. The high voltage side be applied with the small portion of the rating voltage. So here we're using a source transformer. So we use a transformer to get the necessary voltage to input the high voltage side to get the rating currents. So for this transformer, so when we apply the rating voltage, we apply a certain voltage, get a rating currents. Okay, so 20 kVA with a rating powers, 230 volts, and secondary 2,300 and primary. So it's rating currents and high voltage side. Later on show you that will be 8.7 amperes. So the reading and here, so we read 1, the currents input to the coilers, 2, the voltage input to the currents, and 3, the powers inputs to the circuit. Generally, the current in short circuit tests is the rating current. The voltage is a small portion of rating. This is a small portion of rating. 50 volts over 2300 volts equal to, what's it? Okay, very small, right? So this is, right, so 5 over 230, right? That is less than, okay, 4, right? About 4%. Something, right? So we just 200, not 4%, 2.5, 2.4%, something like that. Okay. 2.2. Okay, so just about 2.2. So very small portion, right? Look at here. So very small portion. So this is rating voltage currents. Look at here. Now, so you are asked to calculate what the equivalent impedance, reactance, and the resistance referred to high voltage side. Okay. The equivalent impedance, reactance, and the resistance refer to low voltage side. And the voltage regulation and power factor 0.7, okay, voltage regulation. Okay. Remember, okay, with this in your mind, we're looking at the suggested solutions. First, right, the short circuit tests that input voltage 50 volts, input current 8.7 amperes, input powers 250 volts. In your mind, we have the equivalent circuit, right? Okay, equivalent circuit. So the equivalent impedance, this is equivalent impedance, right? So that's very, very simple, okay? Very simple. Okay, so now refer to the high voltage side. So the equivalent impedance refer to high voltage side. That is the impedance, okay? Impedance equal to the voltage over the current, because this is short circuit, right? Short circuit. So this impedance be 0. So we have the internal impedance referred to the high voltage side. And in this case, so the voltage 50 volts, the current 8.7 amperes. So we can calculate the equivalent impedance of the transformer referred to primary. And the input powers, okay, is the resistive powers here. So the input powers over the input current square, that is the equivalent resistance of the transformer referred to high voltage side. So which has been estimated 3.3 ohms. Okay. So the impedance angles of the transformer, so which can based on the resistance. This is resistance, okay, impedance. So the impedance angle, okay, can be found out, okay, arc cosine R over the Z, so which found 55 degrees. And the reactance can be simply found out. You can use a different way to find out reactance. So impedance, resistance, reactance refer to high voltage side because this is measured at a high voltage side. This is referred to high voltage side. Okay, similarly, so look at here that we can find out the values referred to low because a short circuit test has been carried out at the high voltage side. So we first to calculate the values refer to high voltage side of the impedance, including the impedance values, reactance values, resistance values, even the impedance angles. And when we refer to the low voltage side, so you can simply using that the values refer to the high voltage side over the transformation ratios. Here, the transformation ratio is 2,300 over 230. So that is 10. So you found that the internal impedance referred to the lower side is smaller, referred to the high voltage side is bigger. They have a ratio of their transformation ratio square. Okay. Now, so we're looking at the rated secondary low currents because the transformer rating is 20 kVA. So the 20 kVA over the secondary voltage, that is the 87, 87 amperes. So refer to the lower side will be 8.7 amperes. Okay. Okay. So this is referred to secondary. Okay. So we're looking at the then. Okay. We refer to secondary. So we're using the secondary. Okay. We refer. Okay. Using the secondary currents, secondary referred resistance, secondary referred reactance. We can find out the resistive voltage drops, reactive voltage drops, and secondary currents. And we can find full load, secondary induced, electromotive force, and 0.7 power factor. So this is the secondary induced voltage. It's the secondary full load output voltage plus the secondary voltage drop refers to secondary. This is the ideal one. So then we can find out when it is opened. So this is the secondary output voltage when it is opened. opened. Secondary full load output voltage rating. Okay, so by doing cyclic calculation, what is estimated that is the secondary output voltage when opened, and the difference between the open no load output voltage minus full load output voltage. So V2 here is secondary full load output voltage. So over the full load output voltage, that is the voltage regulations. For this case, voltage regulation can be estimated like this. Once again, the example 7, very important. So based on these examples, I hope that you all have a clear understanding about the transformer equivalent circuit. Also, know how to using the short circuit test results to estimate the internal impedance and of the transformer, refer to both primary and secondary. Also, know how to use the short circuit test results to estimate the voltage regulations for a given transformer. Of course, cyclic concepts once again will be examined when we learn about the three-phase transformers. This is about the short circuit tests, internal impedance, voltage regulations. And example 8 is about how to use in the open circuit test results, short circuit test results to estimate the transformers, equivalent resistance, equivalent reactance, referred to primary or secondary, transformers copper losses, transformers core losses, and transformers efficiency examples. So now we have a quick look at example 8. So here, suppose we have a transformer that has a transformation ratio 2000 300 volts over 208 volts with a rating power 500 kVA, 60 Hertz distribution transformer. So it is tested by means of the open circuit and short circuit test prior to bring out into the put into the service as a step-down transformer, so that to predict its efficiency and regulation. Now, the testing results be listed here. First, the open circuit tests. The open circuit tests, the VL, L stands for the lower side. Okay, so then the meanings of it. So the test result is that the open circuit test has been carried out at the lower side, with the higher side be opened, lower side be applied with the rating voltage. Look in here, so rating voltage. So the open circuit test, the voltage is the rating voltage you supply and obtained a small currents. That's the core, right? Excitations. And the open circuit powers, this is the core losses. Okay. Similarly, that for the short circuit tests, that has been tested at the high voltage side. That means the lower side be short circuit, and the high voltage side be applied with small portion of the voltage. So this is small portion. Okay. Small voltage. Rating currents. Okay. Copper loss and rating current. Got a point? So here I have a clear explanation on the meanings of the parameters listed here. Okay, listed here. So you understanding the parameters meaning of the open circuit test and short circuit test. Then we can calculate the equivalent internal resistance referred to the lower side or referred to higher side. And we can estimate the copper losses or core losses easily. Now, first, equivalent resistance referred to the lower side because the equivalent resistance should be based on the copper losses. And the copper losses, the test has been carried out at higher side. Okay. So from the short circuit tests, the equivalent resistance referred to higher side, that is the resistance referred to higher side, is the powers measured of the higher side input currents, that's the rating currents. So the power is given 8.2 kilowatt over the current given 217.5 amperes square. You got the resistance. But this resistance referred to higher side. The question asks you to get the resistance referred to lower side. So equivalent resistance referred to lower side is the higher side resistance over the transformation square. Here, which becomes smaller. Remember, the resistance referred to lower side is much smaller than that referred to higher side. Okay. B, the lower side resistance, higher resistance, turn ratios. Okay, you ready? So a resistance of lower side only. Now, this is the resistance referred to lower side. Half of it, generally is the resistance of lower side only. Now, actually I explained this one in the example 5. Okay, so the higher side, suppose the higher side, look in here. Generally, we suppose the higher side resistance equal to lower side resistance equivalent refer to higher side. Okay, and we now got so in such a way, so half of the equivalent resistance refer to lower side with lower side resistance. So lower side resistance can be estimated. Okay, and the low side copper loss theory. Open circuit tests. Now here, so open circuit test, because when the open circuit test carried out and lower side, with the higher side be opened. So only the lower side has the copper losses. But here we have a limitation estimation of lower side, right? Copper losses during the open circuit test to see how small it is. So with this right secondary resistance, with the open circuit test currents at lower side, we can estimate the lower side copper losses during the open circuit test. Look at here. So this very small. Okay, in comparison with the core losses, very small. So much smaller than the 1,800 watt core losses actually. So the transformer's exact core losses can be estimated the open circuit tests 1,800 watts, but the internal copper losses during the open circuit tests at the secondary side and lower side is 5 volts. So exactly speaking, the core losses will be 1,795 volt, but almost the right 1,800. Okay, so that's why okay, in the E we said yes, the power obtained in the open circuit test may be used as the core losses. The error is approximate right here is about 0.3. This is within the error produced by the instruments used in the test. So we might assume, therefore, that the core losses is 1,800 watt. Okay, so the example 8, okay, we finished. So today's example 6, example 7, example 8, okay, demonstrate to you how to analyze the transformer based on the open circuit tests and short circuit tests. So the analysis including how to estimate the internal impedance referred to both primary and secondary, how to use the test values to estimate the transformer's voltage regulation, how to estimate the transformer's internal copper losses and core losses. So what is the impacts when we're doing the ignore the core losses, when doing the short circuit tests? What's the impact when we ignore the copper losses when doing the open circuit tests? You should be able to, when somebody asks you about that questions, be able to explain of them based on the equivalent circuit or based on whatever you have understood. So that's the end of today's tutorial. So next week, we will continue to talk about several examples on the three-phase transformers. Okay. So if you still have some questions on the transformers, you can get single-phase transformers. You write to me after the tutorials, or at this moment still have a few minutes. You can use in the chat box to me. If not, you can take a break. Thank you.